In this video, we will discuss the limit of a function, and we have 3 learning objectives. First, know what a limit is. Second, be able to determine the value for a limit. Third, be able to determine the values of a one-sided limit or infinite limits. If you have taken pre-calculus, this is something that would be familiar because you spent a fair amount of time on it. For us, and if you haven't taken pre-calculus, it may be a bit new, please feel free to stop and ask questions. Getting started, we've got to know what a limit is. And you'll note I went and copied this definition directly from your textbook. And if you feel like reading it, go ahead and read a limit. Go ahead and read the definition. Well, right now, if you want to go out loud, you can, but you don't have to read it out loud. But the biggest part about it is it's easier to understand it by comparing a graph and looking at the graphs than it is to actually go through and just read it, because the definition is presented in a somewhat mathematical perspective, still informally, but here's the big idea behind it. If we are starting off and we want to know the limit as x approaches like a 2, we are going to pick values that are, like, for example, say this is the point of x equals 2. We're going to look at values on the left and on the right, and I know I said that backwards, but start considering tracing along the graph as you get closer and closer to this value of 2, what is happening to the height. If we pick x values that are on either side of the 2, they'll come up and give you heights. They come up and give you heights. Get x values that are closer to 2, and you get different heights. Come even closer to 2 again, and you notice how the heights are getting closer together as the x values get closer together. Eventually, we're going to get to a point where we start saying get within like 100 billion digits close. So you're like 2.000000000000000000001. And 1.9999999999999999999. You get really, 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 really close. What is happening to the y value heights? If you have a problem where they are both coming together from the left and the right, eventually they start closing in. As you get really, really close to 2, you get really, really close to this height. That's a limit. Intuitively, as you get closer and closer x values, what happens to the y values? Are they also getting crunched in closer and closer together? That's the limit. Knowing and being able to describe that process is one of our learning objectives. Could you describe a limit as x values get close to a certain picked one? What happens to the y values? This notation is what we wind up using. You'll note how it says x approaches x arrow a. This is telling us as we get x values that are really, 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 really close to a, like barely to the right, barely to the left, as we pick those x values, the y value height of the function is limiting in on some y value. And we use an L for limit of that. This is our notation. When we start putting them together, we would look at pieces like this. Guess the value of a function. We are going to learn many different techniques for how to evaluate limits, for how to work with limits, a lot of pieces. But to start off with, the very first thing that we need to do is actually to pull up the calculator. And I apologize for not getting this piece in advance. We are using the TI Nspire, and basically what we're going to try to do are create the tables like we were discussing previously. If you're using a different calculator, you can of course use a TI 84 or an 83, pretty much anything that has a table feature you can use. So let's get started. For this one, we're creating the graph. And what we'll start by doing is actually typing in the term. This whole piece is what you will type into the calculator. That's the function we will press in. So we have in the parentheses x subtract 2, and then we had in the denominator it was x squared subtract 4. So x squared minus 4. Close parentheses. So there we have our first one. By pressing enter, we can create the graph. Something worth noting. Look over at the x value of 2. All right, and I got to, okay, I'm going to zoom in more. Okay. Okay, so there's 0.1, 0.2, 0.5, 1. Okay, so on this one, each tick mark is counting as a 1. You see this tick mark right over to the right? As we get closer to the left and right, what's happening to this y value? Well, seeing the y value on it is really kind of difficult to do. That's why we will use the tables. If you remember how, bring up the tables. We'll go to Menu, and Table, Split Screen Tables. When you start looking at them, you notice the x values, 1, 2, 3, 4, 5, and it's giving y values. It's a y value of 0.33333, so a third. At x equals 2, the function is undefined. At 3, it's 0.2. So we have numbers 1 and 3 to the left and the right. But we want to start zooming in on them further. So for table, we'll go into Edit the Table Settings. And let's start the table at 2. But then use the table step to be something very, very small, because we want it to be very, very close to 2, such as 0.01. And we can hit enter. Because I'm picking the table to start at 2 because the limit is approaching 2. I could very easily start the table at 0, but then I'm going to have to scroll up 0.01, 0.02, 0.03, 0.04, 0.05, all the way up to 2 to get to the numbers we care about. As it is, for this one, on the table, we can scroll up and down and get values that are pretty close. You notice how we have 1.94, 1.95, 99, 2, 2.01. So here we have numbers that are pretty close on either side. Take a look at the numbers for 1.98, 1.99, 2.01, 2.02. What do those numbers look like they're kind of closing in on? As a guess, 0.2506, 0.2493. It looks like it's closing in on 0.25, so 1/4. Using the table, that's how we could guess our value. We are guessing 1/4, and we're done. For this particular problem, using the technology, using the numerical representation of our function, our tables, we could get the answer that way. Now, of course, we use the calculator to build the table. You could just as easily say, I'm going to pick 1.98 and actually crunch the numbers and create the y value for it. And then you could pick 1.99. You could build the table yourself from scratch. Completely valid technique, but why would you want to? If you've got the calculator which will crunch the numbers for you faster, why would you want to? Our example 2, same process. Estimate the value of this function. Estimate the value of the limit as t approaches 0 of the function t squared, the square root of t squared plus 4, then subtract 2 all over t squared. Well, let's get that typed into the calculator. And I'm going to come up and say menu, actions, table. I'll remove the table and then pick this piece for the graph, tab, and delete the graph. So menu, actions, graph, enter a function, and it was in the numerator, we had the square root of t squared plus 4. We will have to change the variable though, because the calculator doesn't have a function set up for t, it's set up for x. So although we are using the variable t in the problem, for the calculator we'll actually have to type in an x squared. So x squared minus 4, parentheses to close the square root, and then arrow over, parentheses to close the numerator. Except I'm missing something in the numerator. Wasn't there a plus 4? No, this is a minus 2. So I needed plus 4 minus 2. I've got to back this part up because I made an error. Square root of x squared plus 4, parentheses to close the square root, use the right arrow to get out of the square root, then it's minus 2, close parentheses to close out the numerator. All of that we will divide by x squared to get the whole piece. And click enter to get our graph. And we look at it and say, wow, doesn't that look fascinating? But we're going to wind up using the tables to help us out anyhow. So insert a table. And you'll note where we're starting. 1, 2, 3, 4. We'll want to start at 0 because the limit is approaching 0. We are doing limit of t approaches 0, so the table should be centered about 0. So we'll go back in the menu, table, table settings, table starts at 0, and the step, we want to have something pretty small like 0.01. Click enter, and we can scroll up. It's undefined at 0, but what is it closing in on? Looks pretty close to be 0.25 again. Okay, so if you wanted to, you could say we're estimating it to be 0.25. I prefer fractions, so it's a matter of preference. I just like fractions better than I like decimals. I don't know, maybe I'm weird, but that's what I like. But yes, you could estimate it as a decimal if you preferred that one. Okay, example 3. Guess the value for sine of x over x as x approaches 0. Okay, so we'll come back in, and we'll go menu, actions. I don't want resize table. Get rid of the table. Menu, graph entry or edit. I want to edit the function. I don't want F2, I want F1. And I'm just going to go through and delete the whole thing. And so we had sine of x. Use the arrows to get out of the sign. Divided by x. And there's our function. We want to know what happens as the x value approaches 0. Well, I'd like you to look at this particular graph right now and just say, from the graph, what would you guess is the answer? Okay? You might be tempted to simply say, okay, we're done at 1. because it looks completely reasonable. Okay, well, let's continue and say, let's do this table. Plug the table in. We'll go back in, change the settings so that we'll start at 0, and we'll pick 0.01. Click Enter, and we can scroll up, and what are you seeing right around it? Pretty close to 1. Okay, so we can look at the graph and use that as a piece. We could use a visual representation of our function to try to guess the value. We could use the numerical expression with the tables to try to guess the value of our limit. Let's do the same thing for this one, though. Very similar function. How is it different? Yes, this is sine of pi instead of saying sine of x. We'll come back, and I'll get rid of the table. That's what we're going to investigate. Scotty was asking, does it approach 0? And so I needed menu, graph, edit. I want to go back to F1 and scrolling over. Wait, there. Over. Delete. And pi is down by the h, along with a number of our other symbols. So it's good to know where infinity, e, and theta, and some of the other ones are. But sine of pi, click Enter, and we look at it, and it's like, okay, looks like it would be a 0. I'm going to grab this and start coming in closer. Okay, and let's zoom in more. And let's zoom in more. And let's zoom in more. Okay, so when we come back to this piece, we can come and say, put in the table, split screen, and then we'll go menu, and table settings. Table starts at 0, step functions of 0.01. Click Enter. What's happening? 0, 0, 0. Why are they wind up all saying 0? Do you remember what the sine of pi actually is? Yeah, the sine of pi is 0. This is a piece where we actually are saying what is the limit as x approaches 0 of 0 over x. But what happens when it's constantly 0, 0, 0, 0, 0? We wind up with a whole bunch of zeros. So there we have some numerical expression, some investigation. And we're guessing values based on what we are able to see. Well, with this one, what were we saying is the guess? It looks like a 0. Because when we were checking our tables, it was 0, 0, 0, 0, 0 over and over and over and over and over. Okay? Come back to this one. Oh, example 5. Find the limit of x cubed plus cosine of 10x over 500 as x approaches 0. We've got to get it typed in now. So coming back, and menu, get rid of the table, and menu, go back into graph, function, and I want to go this piece, I'm just going to delete it. And then we had, it's x cubed, arrow over, plus, we had cosine, cosine of, it was 3x, wasn't it? Nope, 10x. Cosine of 10x, and go parentheses over, divided by 5,000. And so, there we go. Why can't I see anything? Yeah, because I'm zoomed way in. So d to the 5th. Okay, there we can finally start seeing some stuff. So going back, what does it look like we're closing in on? Based from the graph, yeah, we could say we would take a guess. It looks like a 0. Let's use the table and do some further investigation. Menu, table, split screen, menu, table, settings, and we'll go 0.01 and start looking at right around 0. What are you seeing, though? Does it actually look like it's closing in on 0? It looks like it's closing in on 0.0002. And if we wanted to go further, we could investigate this by using even smaller numbers. Edit the table settings and say 0.001. That's a really small step. And so 0.199, we're at negatives, zeros. And so menu, table start at 0, because otherwise that's going to take a while. And scroll up. What does it look like it's closing in on now? I'd also like to know, why are they all saying 0.0002? Even calculators, even powerful calculators, can only go accurate to so many digits. Especially when we have so much space. What's actually going on here is that we have like 0.000199999, and there's just not enough space to display all the accurate calculations. Or we could have 0.000200003, and they're pieces that are so close that the calculator cannot display the difference unless we give them some more room. It's not that all of these values are actually equal to it. It's just that we're getting rounded and we can't see the difference on the calculator. Even though it looked on the graph like it, we couldn't see the difference for what it actually seems to be closing in on. Example 6. State the Heaviside function. Please note how Heaviside is spelt. It's not spelt H-E-A-V-Y with the word heavy. It's spelled this way because there was a guy who actually created it, and this is how his name was spelled. The Heaviside function is a piecewise defined function that's fairly simple. You could have 0 or 1. And generally it's if your t is greater than or equal to 0, and if t is less than 0. So in this regard, it's just a graph that will look like we have a whole bunch of zeros, and then it jumps upward to a 1 and stays constant like that. That's our Heaviside function. Why do we have a piece why do we have an example that's all about the Heaviside function? Because this thing is great as an example for being able to teach other pieces. When you do some pieces with statistics, when you're working in statistical analysis classes, a lot of times it's nice to have an indicator variable. For example, if you're doing a statistical analysis based on gender, you could have it set up that I'm going to use a 0 for a male, 1 if it's a female. Or perhaps you'd say 0 is female and male is 1. For example, if you're doing a study on NFL players, do you know of any female NFL players? By being able to include the Heaviside function as part of the formula, you can instantly eliminate all women just by saying multiply by 0. It gets used in statistics, it gets used as some examples for Calc, but you should know what the Heaviside function is. OneSided limits. When we were doing the tables, you notice how we were looking at above and below? What if we don't care about above and below? A one-sided limit is a piece where we're saying if you approach the graph only from the left-hand side, like here, if we're approaching only from the left, where is it going? A right-sided limit would be saying if we're approaching only on the right, where is it going? The same concepts are there as what we'd have for a regular limit. If we're discussing a left-handed limit, it's saying as we get closer and closer and closer to this x value coming from the left, what is happening to the y height? This one seems to be getting smaller and smaller and smaller as we are approaching it. But we're approaching this only on the left-hand side. We could do the same limit approaching from the right-hand side, getting closer and closer and closer. In that instance, what is happening to it? We're still getting closer and closer to our y-axis, but as we get close, are they getting close to be the same number on both sides? That's a pretty huge gap, and you can see I'm already pretty close. In particular, as we are getting closer and closer to the left, I need to switch to red, this height is getting really, really close to the height of that open circle. This value, that y value, is the left-hand limit. And if we approached it from the right-hand side, getting to here, this value is the right-hand limit. Are they actually the same? No. We can clearly see the jumping gap in between the two. When we discuss limits, we're talking about as x is approaching some number like 0 or 2 or 5 coming from the left-hand side, the y value is closing in on some number. Or as we come in at an x value from the right-hand side, the y height is approaching a number. These pieces do not have to match. And this past graph is an illustration of that, where they don't have to match. But when we talk about the general limit, where we say f of x, the limit x approaches a equals 5. Well, if we had this piece saying the left-hand limit equals 3 and the right-hand limit equals 5, does it make sense to say this piece? No, it can't, because if we're talking about the limit, the means one limit, one answer. And if we are getting two different values coming from the left and coming from the right, we can't pick and choose and say, well, I guess 5 is the prettier number, so I'm going to call my limit 5. If the left and right-hand limits are not the exact same number, then this piece does not exist. Not all limits will exist. This is a picture where we ran into it. At this point, if we start approaching 2, the limit doesn't exist, because coming from the left, coming from the right, they're not closing in on the same y value height. That's also not the only way that limits could fail to exist. We'll discuss some of those in a little bit. But let's look at a bunch of limits here. You'll notice it's the same graph, but we've just taken and entered a bunch of the tick marks to give us some perspective. So, for part A, as x is approaching 3 from the left-hand side, what is happening to the height? Okay, so here's x equals 3. When we pick x values that are close to the 3, come down to hit the graph, where is the height closing in on? Yes, we've got it. It is closing in on the height of the open circle, so we can come straight over from the open circle and say, what's that height? Understanding that I suck at drawing straight lines, we're guessing about a -2. And if we actually had proper grid lines, we'd be able to see a little bit better, but we're saying -2. Switching colors to blue. As we approach 3 from the right-hand side, what's the graph closing in on? Right at that height of 0, so the right-hand limit as x approaches 3 equals 0. What do you mean? Scotty has asked. I thought we'd use the same line. Yes? Because it's a... When we're actually looking at the function, Scotty, where is the function defined to the left of this 3? The graph is actually down here. So when we're looking for values that are close to it, we've got to come down until we hit the graph. This would be saying at like x equals 2.5, the function f of x, or I'm sorry, g of x is about 1, 2, 3, 4, -5. But you notice how this number is to the left? It's less than 3. Well, we could come in closer and say, as at x equals 2.9, what is the height? At 2.99, what is the height? At 2.999, what is the height? But all of those values, 2.5, 2.9, 2.99, they're all coming from the left-hand side of the x. And we're going down to where the graph is actually meeting. For the right-hand limit, we have the same issue. Instead of using numbers that are a little bit smaller than 3, we're going a little bit bigger, like 3.1, 3.01, 3.0001. So at 3.5, what's the height? At 3.1, what's the height? At 3.01, what's the height? But they're all based on where the actual function is. Better? Thank you for asking a question, sir. I do appreciate it. Okay, part C, the limit of g of x as x approaches -8 from the left. Well, we have 1, 2, 3, 4, 5, 6, 7. Here is -8. And so this is our point for g of -8. How do you approach it from the left? Can't. There is no graph to the left of -8. And so if you don't have anything that's approaching from the left-hand side, you can't talk about a limit. This is an undefined limit. A lot of textbooks will ask you to use undefined. A lot of textbooks, a lot of authors also will use DNE for does not exist. They're two different things. They're basically two different ways of saying the same information. There's no answer. It can't be done. Progressing to the next one, and I'll switch to yellow for this one. What is the limit of g of x as it approaches -2 from the left? Okay, so things worth noting that perhaps are a little bit unclear. This is an open circle. This is the closed circle. This point where it jumps up at the top, that is the actual function value for g of -2. As we are closing in from the left-hand side, where is the function actually going? So if we're at 2.5, it's here. Wow, that's terrible. If we're at negative 2.5, if we're at negative 2.1, negative 2.01, negative 2.001, what is it closing in on? It appears to close in on negative 4. Please note, that is not the same thing as the actual function value. A lot of people try to take advantage of the trick that say, oh, I'm just going to plug in the number to the function and it's guaranteed to give me a correct answer. For certain types of functions, that might work. That'll actually be one of the techniques we talk about. But it is not a guarantee. You can't always just plug it into the function and say it's going to give me the correct answer. This is one where it does not. The left-hand limit is negative 4, but the actual function value is positive 4. Let's look at this one now. The limit, please note it says limit, not left-hand limit, not right-hand limit. It says total limit, so they must match left and right. If they don't match left and right, we've got a problem. So we've already done the piece in the yellow. The left-hand limit seems to be closing in on negative 4. What about the right-hand limit at like 1.5 and negative 1.8 and negative 1.9? They're both closing in on negative 4, so this is one that we can say it appears the limit of g of x as x approaches negative 2 is the limit negative 4. A lot of stuff being said for that tiny little notation, right? Yeah. And last one, we'll switch the limit as g of x approaches 3. I suppose I should do this one in black because I haven't used black yet. What are you saying? A couple people were whispering where they looked at it. As x approaches 3, coming from the left-hand limit looks like it's about, right around negative 2. The right-hand limit looks like it's a 0. This is one that does not exist. Because the left-hand limit and the right-hand limit do not match, the total limit does not exist. So, find this one. Limit as x approaches 0, 1 over x squared. I will note, we could do the same piece that we did before. We could type this into the calculator, but I'd prefer to think of it a slightly different way. If we are taking numbers that are just slightly bigger than 0, like a 0.01, what happens to this when you're plugging in 0.01? Well, 0.01 squared is 0.0001. What happens when you divide by a really small number? It starts getting big. Okay? Well, what if we took, instead of 0.01, we took 0.0001 and squared it? That will give us 0.1234567 What's happening with it? Getting even bigger. What if we were taking from the left-hand side? It's still going to be the same piece, because when you square a negative, you're going to wind up with still the positive number and the positive number. So what's happening with these? This one was actually 10,000. This one was 10 million. And if we took more zeros and added them in, what's happening to the limit? It's getting bigger and bigger and bigger and bigger, so that this piece, as x approaches 0, 1 over x squared is approaching infinity. Does that mean that we would say the limit equals infinity? No. This is a common piece that we would look at. We can never actually equal infinity. Because if we were to go through and say that this piece equals infinity, that's saying infinity is a number. Infinity is not a number that we can actually reach. Even this piece does not say, if we say limit as x approaches 0, 1 over x squared equals infinity, this notation does not say the limit exists. If you have a limit that starts flying up towards infinity or starts flying downward to negative infinity, the limit still does not exist. But we still use this notation that kind of looks tricky, and it looks like we say the limit does exist. We're using this notation only so that we can describe the specific way that the limit does not exist. It does not close in on a finite number L, so the limit does not exist. But this just shows us, hey, at least it's not matching. Writing it out this way says if you come from the left and the right, they're still matching. They're just matching by flying upward toward infinity instead of matching. Instead of one going down, one going up, or going at different numbers or something like that. Okay? What this piece is telling us, though, what it actually says, if we use this notation, it says, I can pick any number I want. If I want to use a million, if I want to use a quadrillion, if I want to use a Google or a Googleplex, pick any big number you want. And you can make this function become even bigger than that. You just might have to get really, really, really close to x. That's all that this piece is saying. So, using this same technique, yes, I know we could start plugging this into the calculator. We could use the tables. I'd like to avoid using the tables and instead use some logic for this. What's going on in the problem? As x is approaching 2, so we're using numbers that are perhaps a little bit bigger than 2. What's happening in the denominator? We're going to wind up with numbers that are like 0.0001 being squared again. Well, in particular, you see the negative out in front? If you catch the negative at the front, that's saying we have a negative here. So yes, we have the same situation as the last one, where if we're picking really numbers that are really, really close, we wind up with negative 0.0001 squared with the negative out in front. Either way, we wind up with this situation where the number portion starts blowing up as big as we want, but because of the negative sign wrapped in the yellow, the actual piece, whoa, that looks cool, the actual piece is approaching negative infinity. Once again, this is saying not that negative infinity is a number, it's not saying that we actually get there. When we say it equals negative infinity, it's saying this graph of f will go to as small a number, as negative a number as we want. Negative 50 trillion, negative whatever. We can get farther down the y-axis as long as we get closer and closer to the x value. What about this one? Find the limit of 1 over x as x approaches 0 from the left. Do you remember what this graph looks like? The graph of 1 over x has this structure to it with my crappy sketching ability. So, as x is approaching 0 from the left, what's happening to the actual function value? So what would we say the limit is? Yeah, we would say that this limit is approaching negative infinity. Doesn't mean the limit exists, just means that it's going down the y-axis. Okay, if we were to switch this, the question is asked, what if the top part? What if we were saying approaches from the right? Well, as we're closing in on the x from the right, the y value is coming, if we use the right-hand limit, it's closing in on positive infinity. So could we actually go through and say that the total limit can we say it equals infinity? Can we say it equals negative infinity? No. Well, you'd like to say, oh, well, what about saying plus or minus? No, not a notation that gets used because, again, if we talk about the limit, we want it to be 1. And plus or minus is not one answer. Nope. It does not exist. This would be a piece that if you wanted to say limit of x approaches infinity of 1 over x, you can't say all real numbers, you can't say infinity, you can't say negative infinity. You just have to say it does not exist, or it's undefined. There's no way to do it. We don't even have a notation that'll take care of it. It's not there. Example 11 is based on these pieces. You'll notice how we have all these ones where we're looking at it. The total limit approaches infinity. The total limit approaches negative. Limits from the left go off to positive or negative. Limits from the right go off to positive or negative. All this piece is saying is if you've got a graph where you have a vertical asymptote, at some point it's going to have to go off toward infinity or negative infinity. If you have a vertical asymptote, you might have both sides coming up to infinity. You might have both sides going down toward negative infinity. That's what vertical asymptotes actually are. Based on your previous classes, how did you find vertical asymptotes? In your previous classes, like in Algebra 2 and Pre-Calc, do you remember saying where do you have to divide by 0? If you are searching for divide by 0, a lot of times that was your clue to find a vertical asymptote. But it wasn't a guarantee. Depending, I'm not sure if you looked at much of them, but there were some of them where you could have a divide by 0 type problem, and there was no vertical asymptote there. We actually encountered some of those earlier in our first couple problems. Remember when we were doing all of, like this one? Or when we were looking at some of these ones, how if we actually tried to plug in 0, I'm not sure if you remember it, but when we did this example, do you remember seeing undefined in the tables? It said undefined because that's where we were dividing by 0. But when we looked at the graph, was there a vertical asymptote? No, there wasn't. It is possible to have a divide by 0 type problem without having the vertical asymptote. That's why we don't just rely on divide by 0, but we actually have to look at the limits. What is happening to this piece as x approaches here? As x is approaching 1 from the left, what's happening to the top? Well, 4 is like 4 times 0.9. 4 times 0.99 times 0.999. 4 times 0.9999999 is closing in on 4 times 1. Specifically, 4 times positive 1. But here, if we are closing in from the left, we have 0.9 subtract 1 would be negative 0.1. And 0.99 subtract 1 would be 0.01 with a negative. Add another 9, you get another 0. Add another 9, you get another 0. So as we get closer and closer to 1, we're adding more and more zeros, which means we're dividing by increasingly small numbers. And because we're dividing by increasingly small numbers, logic would tell us that this is a number that's going to start blowing up to be bigger and bigger and bigger. Well, because there is always a negative on the left-hand side, this is going to blow up, or the numbers will get increasingly arbitrarily large, but they're always negative, so that's telling us it's going off toward negative infinity. That alone would be enough to tell us that we could have a vertical asymptote. On the right-hand side, we have the same issue. 4 times 1.000001 is really close to 4. And 1.000001 subtract 1 is really, really small, but positive. And so this is one that we would have blowing up to be a positive infinity because we are still guaranteed to have 2 positive numbers. And the last one we have, find the vertical asymptotes of cotangent x. Please remember that cotangent is cosine of x over sine of x. And so what we're looking for, when will this limit wind up being, when will the limit wind up going towards a negative infinity or a positive infinity? Well, like we noted here, if you wind up having a divide by 0 situation, that is one potential spot because you could have negative numbers you're dividing by to make it blow up. You could potentially have positive numbers that you're dividing by to make it blow up. That's the same type of piece. We could wonder, when is this denominator going to equal to 0? Because if we are on numbers that are tiny little bit less than 0 or a tiny little bit above 0, as we start limiting in on the x of 0, that's going to tell us that the limits are going to go off to positive or negative infinity. The limits blowing up are what tell us that we actually do have asymptotes. So here is our graph of sine. At 0, we have the sine function has this, well, my drawing's kind of crappy, but we can tell the basic idea. At each one of these points, those are what we're looking for. You remember on the unit circle that the sine was the height of the right triangle? This height right here is sine. So for which angles do you have a height of 0? Well, you have 0. And then to the other side, you have pi. You come around again, you have 2 pi. Come over to the left again, you have 3 pi. And come over again, you've got 4 pi. Come around again, you have 5 pi. If we started rotating to the left with negative angles, we'd have negative pi, negative 2 pi, negative 3 pi, So what we wind up with, the sign of x is going to approach 0, which will cause the limits to balloon up to positive or negative infinity whenever an x value is equal to k times pi, where k is an element of the integers. There we go. This set will tell us the locations for all the vertical asymptotes, which finishes our problem off. Please remember the learning objectives for today. You should know what a limit is. You should be able to describe it that as you close in on the x value, the y height is going to close in on some finite number L. You should be able to use a graph, use a table, use logic, but you should be able to determine the value of a limit, including if it's a one-sided limit, closing in on a finite number, or if it's a limit that balloons upward or downward to positive or negative infinity. You should be able to do those things. Of course, the infinite limits are also used to determine the vertical asymptotes.